Hi everyone. In today's video, I'm going to talk about Sherman-Morrison-Woodbury identity. So essentially, this identity is very useful in machine learning, where A is a huge matrix. Let's say we are thinking about A is an uh, D by N by N matrix. Basically, A is going to be a very huge, something like maybe the, for the sake of this discussion, consider it like a 100 by 100 matrix. So if A is an N by N matrix, and then UV are relatively smaller matrix in terms of let's say U is an N by D matrix, and V of or maybe N by call it a K matrix, N by K matrix. This is how it's usually told. And then V is also a N by K matrix, so V transform is going to be a K by N matrix. So UVT transform is also an N by N matrix, so we can add these two matrices and mentally assume K is a very small number compared to N. The key idea is, and let's say we know the inverse of A because we have already calculated it in our previous steps. It's very easy to find the U inverse or V or U because they are a smaller matrix, and it's easy to multiply these matrices with other big matrix. If you want to try to find the inverse of this matrix, then it's going to be a very huge n cube order of operation. So how do we reduce it? Is using this operation, this identity. Instead of calculating this big calculation, we already know A inverse, and these multiplications are small because U is a very small matrix, and so are this VT, A inverse is already known, etc., etc. So we are going to prove this identity and make sure you have more exercises to do on this Woodbury identity so it settles down in your mind. So I will go ahead, and the way to prove this identity is to post multiply first with these guys so as to get rid of VT and A inverse. So if I post multiply both sides with A and VT inverse, then we get A plus VT U VT inverse times, I first multiply by A and then VT inverse. So we will get here A inverse multiplied by A becomes identity, and then we have a VT inverse here, and minus A inverse U I plus VT A inverse U whole inverse, and then you multiply A inverse with where A is an identity matrix, and then again that multiply that with VT inverse, you get identity here. So far with here, the next step to prove that would be to multiply this whole equation by this. So we get A plus U VT inverse times A VT inverse multiplied by this I plus VT A inverse U equal to, and then we are multiply this whole thing with this without the inverse, so we get VT inverse multiplied by I plus VT A inverse U minus A inverse U. So this multiplied by its inverse becomes I, and then the next step is to bring this guy inside, so we get A plus U VT transform minus 1. This is A VT inverse, and then Vt inverse multiplied by Vt is identity, and then A multiplied by A inverse is again identity. So we have only just U here, and then this thing becomes, and I bring Vt inverse inside, so becomes Vt inverse, and Vt inverse into Vt is simply I, so this becomes plus A inverse U, and then minus A inverse U, and this A inverse U, A inverse cancels out, so we just have Vt inverse here. Started looking simplified. I'm going to multiply this whole thing with this particular thing, so this becomes this multiplied by A plus U Vt equal to identity. So I get A Vt inverse plus U equal to A plus Ut U into V transform multiplied by V transform universe. And then if I multiply this by this, we get A V transform universe, and then plus UVT multiplied by UVT inverse is plus U. So both sides are equal, so this Sherman-Morrison-Woodbury identity is proven. And then in the next video, we will go over some of the problems and see how it's useful in kind of deriving the inverse of a matrix derived from one big matrices. Very useful in machine learning. If you do not know me, my name is Vikas Shukla. The best way to connect with me is using my LinkedIn profile that I will leave in this YouTube. And I'm a co-founder of Moonpreneur. Our objective is to make sure that students today are preparing for the future of technology, future of sciences, where the future is headed. Thanks for watching.